Hello, today we are going to talk about ionic bonding. So I think everyone by this point knows that ionic bonding is the giving and taking of electrons between two atoms. Now, this could be the same two atoms, or they could be different atoms. And ionic bonding is different from covalent bonding in the fact that covalent bonding is going to share, where these are literally trying to achieve 8 valence electrons by either giving their outermost shell or taking their outermost shell. So a good way to visualize this is using the electron dot structure. And this is going to be using the number of valence electrons in the outermost shell. Okay, and we can find this information using the group number on the periodic table, which is the ones that go across the top, and we're going to be looking at those numbers more throughout this video. And basically we're trying to get those numbers to equal 8, and we call this the octet rule. Okay, and this holds true for both ionic and covalent bonding. The octet rule just is that every atom wants 8 valence electrons. Okay, so it wants to be full, whether that means losing a couple, losing 1, 2, or 3, or gaining 1, 2, or 3. Okay. Alrighty. So in order to look at this electron dot structure, we would have to write the symbol of the element. So we'll just do salt. I have a couple of pictures of some actual salt cubes here, and this would be more of a molecular drawing of an ionic bond of the NaCl. Okay, and so sodium, since it's in group 1, has 1 valence electron. Okay, so the most we could have in this outer shell would be 8. Okay, and then like chlorine, for an example, would have 7 because it's in group number 7. Okay, and you always go clockwise, kind of like you build in the Aufbau diagram. You go one at a time. And so we can see right away that sodium has 1, and so the best way for him to get 8 valence electrons would be to lose an electron. Okay, so he's going to be the one that's giving the electrons, where chlorine, his easiest way to 8 would be to gain 1 more because he has 7. So he is going to be the taking part of this relationship. So we definitely know this is an ionic bond. We also know this is an ionic bond because we have a metal over here, and if there's a metal involved, we know it's going to be an ionic bond. So covalent bonding is going to primarily be held in the p block between gases, where ionic bonding is going to be with a metal and a non-metal. So that's always another way that you can tell that it is an ionic compound. Okay, so this is an easy way to see the amount of electrons, and because basically no matter what two atoms you look at, when they collide and when they're getting ready to bond, the first thing that interaction they have is between their outermost shells. So we could have magnesium here. If you look on the periodic table, magnesium is in group 2, and so it has 2 valence electrons, and say it bonds with something like chlorine. Okay, now remember, I've said this in class, but if you have something like this, you can't think of just one magnesium atom being picked up and saying, okay, this one magnesium atom has 2 valence electrons. This is a sample of magnesium, and all of the samples have 2 valence electrons. And a sample of chlorine, all of them having 7 valence electrons. Okay, so we'd first move this one over. We can see that magnesium, easiest way for it to get to 8 would be to lose. Okay, and then chlorine is happy, but magnesium still isn't happy. And so with that idea of a sample of chlorine, we know that there is another chlorine hanging out somewhere close by. Okay, and so there would be another chlorine with 7 valence electrons that magnesium could give its other electron to. And this idea right here is really the basis, this metal, non-metal, the basis of writing the chemical formula. Okay, so here we had a 1-to-1 ratio. Both became happy, so we know our chemical formula then is NaCl. Where here, to make everything happy, we know we need 2 chlorines to satisfy every magnesium. Okay? And so, you know, you can think about this in a ratio. If you had a sample of 1 gram of magnesium, you would have to have 2 grams of chlorine to satisfy and to make a complete reaction. Of course, we'll get into reactions and stuff later, but for now, the chemical formula we know then would be magnesium, we need 1, and then there would be 2 chlorine. Okay, and so we'd put a subscript here. This little number here is called a subscript. Okay, and this tells us how many chlorine we have. Okay, and then if there's nothing here, we assume that it's 1, but we would never write a 1 after the magnesium. That's just kind of a common rule. Okay, and so when we are doing this, we're actually forming little ions. Okay, because when we start out, sodium has 11 electrons and it has 11 protons. Okay, but when it's giving away one of its electrons, now it has 10 electrons and it has still 11 protons. Because remember, if you change the number of electrons, triangle means change electrons, you make a bond. Okay, and if you change neutrons, this is from last chapter, if you change neutrons, you make an isotope, right? And if you change protons, then we would be making a new element. Okay, so right now we're talking about bonding, and so we are talking about changing the number of electrons. So if we change this number of electrons, sodium gives 1 away. Now sodium has 1 less electron than it does proton. And protons are positive, right? And electrons are negative. So therefore, its overall charge is going to be positive. Okay, so sodium is going to be this positive 1 charge. Where chlorine started out with 17 electrons and 17 protons, because they're always neutral before, and then it gained 1 electron here. So now it has 18 electrons that are negative, and it has 17 protons. So now this makes chlorine, its overall charge is going to be negative. Okay, and so this is essentially what holds these ionic bonds together, is this positive to negative attraction. And so if you look up here, these are actual little atoms of sodium and chlorine. Okay, and we know that sodium has a smaller atomic radius, so we know that these little purple ones are sodium and these bigger ones are chlorine. There's a 1-to-1 ratio, and they're just literally attracted to each other magnetically with that positive and negative charge, and they form a cube. Okay, and so this is why we get these blocks of salt in this way, because whatever the structure is of an ionic compound, which we'll talk about this when we talk about properties, but whatever the structure looks like at its most smallest molecular level is what it's going to then mimic when it goes into its crystalline state, which these ionic bonds most of the time make some kind of crystal. Okay, so we have these positive ions and these negative ions, depending on if it gains or loses an electrons, and we call the positive one a cation. And this is easy for me to remember because I love cats. Okay, you guys all remember me very upset about my cat passing away. So I love cats, and so cats are positive to me. Okay, Mr. Fitzsimmons, of course, he would disagree with me because he's more of a dog person, but agreeing with me in this case would give you a way to remember this for your test. Okay, and then negative ones are called anions. It's your anti-something. You're negative about it, right? So anions are negative. So we will be referring to all of these negative ions as anions from now on, and positive ones as cations. Okay, so let's look at the periodic table here and see if we can't make some assumptions about what the ions are actually going to be. So we have group 1A, group 2A, okay, group 3A, 4A, and I would highly suggest, 5A. In fact, I think I will post a blank periodic table that you can take notes on for this section. So if you are not taking notes on a periodic table, you should go print that and do that. So right here in the middle, I'm going to write this oxidation number, and we're going to learn about these here in next lecture. And the idea of an oxidation number is that we can't tell the number of valence electrons, and so there is a special thing called oxidation numbers that we're going to have to write in our chemical names to tell us how many electrons these have on their outermost shell. Okay, but we know all the A group here. Okay, and just like we looked at sodium, he lost this one electron, and so he forms a positive ion, positive 1 ion, because he's always going to lose 1. There's no other option for sodium. He's not going to gain 7 electrons. So he's because that would take way too much energy. So group 1 is always going to be positive 1 ions. Group 2 is always going to be positive 2. Group 3 is always going to be positive 3 ions. And in group 4, we save this group for covalent bonding. So they can be positive 4 or negative 4, but technically we're not going to deal with them until we get to covalent bonding. And group 5A, kind of made a mistake there, but you see 5A. Now here's where things change. Now if you have 5 valence electrons, it's now easier for you to gain 3 electrons than it is for you to lose 5. And so these, in this group, all of these are going to be gaining 3 electrons to become happy. So these are called negative 3 anions. This one is 6. We want 8, so he's going to be gaining 2. So he's going to be a negative 2. This one only lacks 1 of having a fulfilled octet rule here. So he's going to be a negative 1 anion. And of course, our noble gases, they are happy, and this is what everybody wants to be like. This is why all this bonding occurs, is because they want that glorified 8 electrons in their outermost shell, that noble gas electron configuration that we talked about last chapter. And there's actually a shortcut. So I want to give you an example here. If we have aluminum, okay, and oxygen. Okay, so let's do the same thing we did with magnesium and chlorine and sodium and chlorine in the last slide. We know that aluminum has 3 valence electrons, so we're going to write the electron dot structure like this. We know oxygen has 6 valence electrons, okay? 4, 5, 6. Okay, so we can start giving them and kind of trying to look at what our chemical formula is going to be. And so here we see that oxygen is now happy, but aluminum's not, so we need another oxygen, right? And so now aluminum goes over here. Now aluminum is happy, but now oxygen's not, so now we need another aluminum. Okay, and so now this guy comes over, and now oxygen's happy, but now aluminum's not. Okay, so now we have 1 more oxygen, and here finally they get even, and all of them will eventually. But this is a really long process using that electron dot structure to draw something like this out. It's great for visualizing the actual ionic bond, but it's not really practical to use for every single problem. And so there's a little easier way, and it's called the crisscross method. Okay, in the crisscross method, we use the charges, and that's why I'm talking about these cations and anions. So we use the cation and anion to write the chemical formula. Okay, so now if we want to use aluminum, we'd come over here to aluminum. Instead of using the valence electrons, we're going to look at the charge, and so it's a positive 3. So we'd write Al with a positive 3, and the charge always goes up. Now the subscript goes below down here, and the charge always goes on the right hand side up with the charge in front. Okay, but these charges never go into your final answer, okay, into the final formula. Okay, we never have a charge in a formula. Okay, and here this is just, we're trying to figure it out, so we're going to show our work here. Okay, so oxygen is a negative 2. Okay, and you'll be able to use your periodic table test, but you don't need to like memorize these necessarily, but you need to understand why this is a negative 2, because oxygen is typically going to be gaining 2 electrons and they're negative, so he's negative 2. So what we're literally going to do, this is called the crisscross method, and so we're going to crisscross the charges using the numbers, not necessarily the charge. Charge isn't any of importance, although you always want the negative one on the right and the positive one on the left. Okay, and that's going to tell you your right and left, but we do not cross the positive and negative down. So the 3 literally goes over here, and the 2 literally goes over here. Okay. And so our formula then is Al2O3. And this always works. So the same way that this is Al2O3, except we didn't have to do all that. All we did was we knew the charges and we crisscrossed them and we get the same answer. Okay? And you can do this for anything. So let's do for all ionic bonds better. So if we took calcium, and we took, let's say we took nitrogen. Okay, so we know nitrogen is a -3, so it's going to be on the right here. Calcium is a +2. So now the 2 is going to go on the other side of the N, and the 3 is going to go on the other side of the calcium. So it's Ca3N2. Okay, so that's just a really easy way to do ionic bonding formula writing. Okay. All right. There is another type of ion called the polyatomic ion. And the polyatomic ion, it acts just like the ions that we talked about in the last slide. And in fact, these ions that we are writing out here and the ones that we are labeling are called monoatomic ions, because mono meaning one, okay? And these are called polyatomic ions. So poly meaning many, okay? Atoms, atomic. And then ions literally means charge. So many atoms with a charge, and that is what a polyatomic ion is. Okay, and these are something that you're just going to have to memorize. Okay, and this is the quiz that we're going to be having on Thursday of this week. Okay, so let's talk about what the polyatomic ion is. It's actually a covalently bonded molecule, and we've talked a little bit about covalent bonds. They're sharing electrons. And what the deal is that these particular covalent bonds are unhappy. So we were talking about that ozone molecule that was the 3 oxygens. And it might look okay, but we know that oxygen doesn't like to be in this state. And because of that, his electrons are constantly moving and changing the structure. And when structure changes with the same 3 molecules in covalent bonding, we call that resonance. Resonance structure. Okay, and we're going to talk a lot more about resonance structures in the covalent bonding chapter. But I just kind of want to give you some background about these polyatomic ions. So what this is O3 has a resonance structure, which would be the fact that it can double bond on the other side. Both ways is correct, and they both have the same amount of electrons, and neither one really are happy with the way that they're bonded. And that's the same thing as what's going on here. So if we just pick one, if we use phosphate here, PO4, so there's 1 P, and then there's 4 oxygens. Okay, and you guys can probably already tell that the oxygen is not happy because it's not double bonded and it has 3 lone pairs instead of 2. Okay, and this is what I was talking about. So this right here, this molecule is actually, these electrons are moving, dropping it down into that double bond for a little bit, and then the electrons actually go onto the phosphorus, and they're constantly flipping. And for a second, phosphate actually thinks that it has gained 3 electrons. Okay, so just like in the group nitrogen, okay, we could actually say that PO4 was also a -3 ion. Okay, so PO4 would be over here, just like hydroxide, which is also on that chart. It's a -1 ion, so it's going to bond with similar things like fluorine and chlorine and bromine. Okay, so what's nice is after you have these memorized with their charges, you can go ahead and do the same thing that you did with the last one, with the ions, the crisscross. Okay, so now if we have calcium phosphate, okay, we know this is -3 and this is a +2 charge. Okay, and now we can flip these two. So now we know we're going to have 3 calcium and we're going to have 2 phosphates. Now the only tricky thing here that's different from the last one, instead of just pulling the 2 down, so if we did that, that would show that we had 42 oxygens, which is impossible. So what we want to say is we actually have 2 of these molecules bonded to 3 calcium ions. So how we show that is we put parentheses around this. Of course, then we would want to get rid of the charges. And our final answer would be Ca3 parenthesis PO4 parenthesis 2. Okay, so these charges act in just the very same way as those cations and anions in the that we were talking about on the last slide. Okay, now a couple things about polyatomic ions is their endings. Okay, most of them are either going to end in an ITE or an ATE. Okay, now there's a couple exceptions. There's a hydroxide ion, okay, and OH, he's a -1 charge, and this one, he's going to be really important later when we're talking about bases. Okay, the acids and the bases, all bases have the ending of OH. Okay, so he's going to be really important to us later, this chapter. And then most of the rest of them are going to have ATE endings. Here's another "ide" ending, okay. Ammonium, that's a unique ending, but he's one of the only cations that we have on the table. So, but most of them are going to be ATE or ITE, and this is actually a very useful thing. This isn't meant to be confusing. This is very useful. So, basically, there's some prefixes here. This is just to help you memorize them, okay? And then here's the suffixes, okay? And what this is so like let's take the chlorates. Let's look right here at this area right here. Now you see some of these have per on the front. It's not a lot. Now this is by no means all of our polyatomic ions. This is just some common ones. Okay, so you'll definitely need to copy down this table. This is the table I'm going to be quizzing you over. Okay. So when you see hypo, this is the lowest number of oxygen. So if we look up here, we have hypochlorite. Okay. So if we just put chlor in here. So hypochlorite has the lowest number of oxygens, and so that would be in this case 1. So if you memorize one of these, if you just memorize hypochlorite, and you remember that that's ClO and it has a negative charge, okay, with 1 oxygen, you know that they're always going to be 1 more oxygen from that. So chlorite, then, without even having to memorize it or look at your chart, chlorite is going to be ClO2, and it's always, the charge is going to stay the same, okay? So chlorite, sure enough, there's 2 oxygens, and as you might guess, 1 more oxygen is added to the 8. So chlorate has 3 oxygens. So chlorate has a formula of ClO3. So this is chlorine bonded with 3 oxygens, still has a negative charge. And then per in the front, perchlorate, which is right here, has 4. Okay, so if you see the perchlorate, we know it is ClO4, still has that negative charge. And this works with any of them. So maybe it's sulfate. Okay, so hyposulfite would just have 2 of the 2 oxygens. Now, it might not always be 1 to start off with. Okay, so you can see sulfite up here. Sulfite, the one that goes right here, has 3 oxygens. So the hyposulfite would have 2. sulfate has 4 and persulfate would have 5, okay, which doesn't exist, but that's one way to help memorizing these a little easier. So if you see ATE, that means it's going to have more oxygens than the ITE ones. So just like this, nitrate has 3, nitrite has 2. Okay, and we're going to be working with these a lot for the rest of the term. So really memorize the charges versus the how to write them out, and also the formulas. Okay, because what's going to happen is you're going to see something like on your test that says calcium bicarbonate, which by the way is baking soda, right? Yeah, calcium bicarbonate. Yeah, I think so. Anyway, calcium bicarbonate, you're going to say that's Ca with a +2 charge. Okay, bicarbonate is HCO3 negative charge. So when you go to crisscross their charges, you know you need 2 of these and only 1 of those. So your final answer would be, oops, I'm going to be out of room here, Ca parenthesis HCO3 parenthesis 2. Okay, so these polyatomic ions are very important, and make sure you study them for tomorrow. All right, have a good evening.